Satellite communication uses microwave signals, but instead of terrestrial towers, the relay is in space. There are three main types of satellite orbits. GEO, geosynchronous Earth-orbiting satellites, are positioned at an altitude of 35,786 kilometers directly above the equator. They orbit at the same speed as Earth's rotation, so they appear stationary from the ground. This makes GEO ideal for television broadcasting and weather monitoring. However, the great distance creates significant propagation delay, about 0.25 seconds one way from ground to satellite, meaning a round trip takes about 0.5 seconds. For voice calls, this delay is noticeable and can be disturbing. LEO, low Earth orbiting satellites, fly at 320 to 1,500 kilometers. They circle Earth in about 90 minutes in polar orbits. Originally used mainly for remote sensing and imaging, LEO has been transformed in recent years by massive constellations like SpaceX Starlink and OneWeb, which use thousands of LEO satellites to provide global broadband internet with much lower latency than GEO, typically 20 to 40 milliseconds. MEO, middle Earth orbiting satellites, are at altitudes of 10,000 to 20,000 kilometers. The most famous MEO system is GPS, the Global Positioning System, at about 20,200 kilometers. Unlike GEO, LEO and MEO satellites do not maintain fixed positions relative to the ground and require tracking or handover between satellites. The satellite's key component is the transponder. It contains a receiving antenna to pick up signals from the ground station, a broadband receiver, a frequency converter that shifts the signal to a different frequency for the downlink, and a high-powered amplifier to send the signal back to Earth. A single satellite may carry dozens of transponders. On the ground side, a transmitting station sends data through a baseband processor, an up converter for frequency shifting, a high-powered amplifier, and a parabolic dish antenna. The receiving station reverses this process. Satellite systems operate in several frequency bands. C-band uses about 6 GHz for the uplink and 4 GHz for the downlink. It is widely used for commercial TV and VSAT networks. Ku-band operates at around 14 GHz up and 11 GHz down, requiring smaller antennas than C-band. Ka-band uses about 30 GHz up and 20 GHz down, offering the highest capacity but being more susceptible to rain fade. L-band at 390 to 1550 MHz is used for mobile satellite services like GPS and maritime communications. Satellite communications serve many applications. Long-distance telephony was one of the earliest uses, with the International Intelsat Consortium connecting countries worldwide. Television broadcasting is perhaps the most visible application. Direct-to-home satellite dishes receive free or encrypted channels via C-band or Ku-band from GEO satellites. Navigation relies heavily on MEO satellites, with GPS providing precise positioning for vehicles, aircraft, and smartphones. VSAT, very small aperture terminal networks, use small dish antennas of 0.6 to 3.8 meters in a star topology, connecting remote sites to a central hub. VSATs operate in Ku or C-band and are essential for banking, retail, and corporate networks in remote areas. The biggest revolution in satellite communications today is LEO broadband internet. Starlink alone has deployed over 6,000 satellites, providing internet access to users in remote and underserved areas at speeds of 50 to 200 megabits per second, with latency comparable to terrestrial connections. This was unthinkable when satellite internet meant GEO with half-second delays. Let us calculate the propagation delay for a GEO satellite link. Given A geosatellite at an altitude of 35,786 kilometers. The speed of electromagnetic waves is approximately 300,000 kilometers per second, the speed of light. Step 1. Calculate one-way delay. Delay equals distance divided by speed. Delay equals 35,786 divided by 300,000, which equals approximately 0.119 seconds, or about 120 milliseconds. Step 2. For a ground-to-satellite-to-ground path, the signal travels up and back down, so the one-way ground-to-ground delay is about 0.24 seconds, or 240 milliseconds. Step 3. For a full round trip, when you say hello and wait for the response, the total delay is about 0.48 seconds, nearly half a second. This is why GEO is problematic for voice calls and real-time applications. In contrast, a LEO satellite at 550 kilometers has a one-way delay of only about 1.8 milliseconds, making LEO ideal for interactive applications. Let us review. GEO satellites at 35,786 kilometers appear stationary but suffer 0.24 second one-way delay. Ideal for broadcasting and weather, problematic for voice. LEO at 320 to 1500 kilometers offers low latency and now provides global broadband via constellations like Starlink. MEO at 10,000 to 20,000 kilometers hosts GPS navigation. Transponders convert and amplify signals between uplink and downlink frequencies. Key bands: C-band for TV and VSAT, Ku for direct-to-home, Ka for high capacity. VSAT networks connect remote sites in star topology. The LEO broadband revolution has transformed satellite from a high-latency last resort to a competitive broadband technology. In the next lesson, we will explore fiber optic communications. Snell's law, total internal reflection, and single-mode versus multi-mode fibers.